Welcome to Down the Rabbit Hole with Eric Ebersol.
Your phone says third floor, but you're crawling up a smoky stairwell and the GPS has gone quiet. A tiny sensor quietly holding position for a few extra minutes could change whether someone finds you. Let's take a look.
Right, that image lands. Today we're unpacking what makes a sensor quantum, where that extra sensitivity actually helps, and 3 practical things you can try in a classroom or weekend tinkering session.
Okay, quick core idea. A quantum sensor uses a small quantum system, like an electron spin or an atomic transition, as the thing that reacts to the world.
Like a tiny detector that whispers when it's nudged? I hear that.
Exactly. Spin or superposition shifts in measurable ways, and that shift can be far more sensitive than a spring or coil in a classical sensor. The payoff is detecting smaller signals or doing it with less power.
A helpful classroom image I use is a tightrope walker versus a plank. The plank is steady and simple. That's classical. The tightrope walker feels every little breeze. That's quantum. Much more sensitive, but you have to manage balance differently.
Experience shows that analogy clicks fast. Now let's move toward where this sensitivity matters in everyday-ish settings: navigation and timing, medical and biosensing, and environmental monitoring.
Start with navigation. GPS is amazing, but it fails indoors or underwater. Quantum accelerometers and gyros promise lower drift, so a device can dead reckon longer without a fix.
Picture a firefighter's tablet, keeping them within a few meters of a known entry point for, say, 3 minutes after GPS drops. That's the kind of real-world window people are targeting. Cheap IMUs might drift multiple meters in that time. Higher stability modules or quantum-grade approaches could keep you within tens of centimeters on the same timescale.
Wait, how realistic is that right now for schools or hobbyists? Are we talking future lab gear or something a teacher can demo next month?
Good question. Short answer, mix. Some quantum-inspired modules and high-quality IMUs are already cheap enough for classrooms. True lab-grade quantum sensors are pricier, but you can meaningfully demonstrate the principle with affordable parts.
For example, concrete parts. Look for magnetometer breakouts like the QMC 5883L or HMC 5883L, often in the $5 to $15 range. And IMU boards like the MPU 9250 or ADXL 345 for under $20. You'll see raw noise and field structure differences right away when you map around coins, speakers, or a laptop.
And for people who want to explore quantum-specific kits, search for NV Center Diamond Magnetometer educational kits or vendors that sell small optical magnetometer demos. Those cost more, but they show real quantum readout in an accessible format.
Medical sensing is the second area. Sensitive magnetometers can pick up faint magnetic signals from muscle or neural activity without huge cooling rigs. That doesn't mean home diagnosis, more like more portable research-grade monitoring and earlier detection in point-of-care settings.
Right, and environmental uses include detecting buried pipes, tracking soil moisture indirectly, or sensing low concentrations of gases when a sensor is paired with the right chemistry. The common thread is sensitivity plus low power operation in the field.
Okay, hands-on pathways. 1, a magnetometer mapping activity. 2, a timing/drift test. 3, use a simulator to visualize how noise affects readings. We owe listeners specifics, so here they are.
Magnetometer mapping. Give students a QMC 5883L breakout, a cheap Arduino or microcontroller, and a handful of objects. Have teams map field strength and sketch contours. Then swap in a higher sensitivity module or run a simulated higher resolution trace and compare.
Timing/drift test. Use a microcontroller and a basic IMU to dead reckon a short walk for 3 minutes. Log the position, then compare against a reference. In low-cost IMUs, you'll often see meter-scale drift appear in minutes. That's the detective work students love, watching error grow and asking why.
Simulators. If you want a quick visual, try browser or Python tools that simulate sensor noise and quantum dynamics. Qtip.org, has examples for quantum systems, and there are IMU drift simulators online if you search IMU drift simulator. These help make the invisible visible.
I can already hear teachers plotting a lesson where one group intentionally walks in a weird pattern and the other group tries to correct for drift. It's fun, and it teaches the trade-offs.
We should call out trade-offs plainly. Cost, calibration, and complexity. I'm not sure I buy the headline that quantum sensors will replace classical sensors everywhere. They excel where sensitivity or new measurement types change decisions. They don't beat simplicity and robustness for everyday tasks.
Totally. So a quick teacher rule of thumb. Ask whether more sensitivity, smaller size, or lower long-term power will change what you can do. If the answer is yes, try a targeted kit or module. If not, stick with classical sensors and save budget for other classroom needs.
Before we close, 3 actionable next steps. 1. Run the magnetometer mapping demo with a QMC 5883L or similar breakout. 2. Perform the 3-minute timing/drift experiment on a microcontroller. 3. Pick a single beginner-friendly quantum or high-stability module to inspect and read one tutorial or review before buying.
1-sentence checklist. Will improved sensitivity, a new measurement type, or significantly lower long-term power change the outcome of your project? If yes, dig deeper. If no, keep iterating with classical tools.
We put starter links in the episode notes. Breakout module sellers, a few beginner kits that demonstrate NV center magnetometry, and simulators like Qtip and IMU drift tools. Experience shows sharing lesson plans shortens the learning curve for everyone.
And a small caution, don't oversell quantum as magic. Teach the cool demos and the calibration or cost headaches alongside them, so students learn both promise and limitations.
If you try any of these, we'd love to hear how it went. Subscribe for more practical science ideas you can use right away, and don't be afraid to learn.
You've been listening to Down the Rabbit Hole with Eric Ebersol.